morning, everyone. Thanks for coming, especially after this wonderful evening we had, and wonderful dinner. It's really a pleasure to be here, and I want to thank Stefan and the other organizers for this invitation. In fact, it's many times I've been in Nancy now, ever since Snow #1, and in this time we've had 9 students go between Nancy and NYU, and that's been a really great pleasure. 7 from École de Mines, and we have 2 PhD students who have worked together with us, so that's been a great thing. So it's really like coming home now. We have our favorite restaurants, favorite wine bars. So today, Stefan asked me to give a little bit of an introduction to SpinTorques, and I'll do that quickly. For those who are new to this, a lot of the slides I'll present, I'll make available so you can look that over. And I'm going to talk about 2 new things, one very new thing in my group, which is our ability now to time resolve the dynamics in perpendicular tunnel junctions through resistance measurements where we drive these junctions above the threshold current, so we can look at dynamics. Things actually we started to do many years ago with spin valves with Eric and Stefan. So the people, so there's several people that have been involved in this, and I'm highlighting those who really contributed to the work I've presented today. Gabriel Chavez, Christian Hahn, who's been working on the tunnel junctions, who was a PhD student in SPEC with Gregoire and Olivier Klein, and Daniel Pina, who did a lot of the theory, which I'll talk about later. And we've been collaborating with BBN. These are experts at low temperature measurements and fast measurements. In fact, they do a lot of work on quantum computing, and they've helped us to do some very fast measurements on particular types of spin valve structures. And we have a close collaboration with a company that came out of NYU, that came out of my group, and the folks there. Georg Wolf is a postdoc at NYU Bartek as well. Steve Watts and Mustafa Pirnabasi, who's the CTO of Spin Transfer Technologies. Okay, so I'll give this short introduction to spin transfer torques, and then I'll go into the studies we've been able to do on perpendicular magnetic tunnel junctions, and being able to resolve now in single shot measurements the dynamics, or at least the projection of the dynamics. If I have time, I'll talk about the work about processional switching in a geometry that you saw yesterday, where you inject spin polarized electrons that are polarized orthogonal to a free layer to induce fast dynamics. So I was very excited to see the switching results yesterday that result from the ultra-fast pulses. And this relates, of course, to processional dynamics. Everything I'm talking about now is happening on timescales associated with the magnetization dynamics. Okay, so this is this field started essentially with the discovery in 1996 by Slanzewski and Berger, a prediction, a theoretical discovery that you could influence the magnetic orientations through the flow of spin currents. And for that, they received the 2013 Oliver Buckley Prize for predicting spin transfer torque and opening the field of current-induced control over magnetic nanostructures. And it's important to remember that prior to that, the only way we could act on a magnet was through a magnetic field, so another magnet or a current. So this really was a very important discovery. In fact, the discovery, if you go back, goes back to even a paper that John Slanzewski wrote in 1989 on magnetic tunnel junctions and the interactions you have when you apply a bias to a magnetic tunnel junction. But this is the year we're celebrating 20 years of spin torque, and I know there have been several conferences around this one that mark that important anniversary. So this is the paper that has many of the basic ideas of spin torque. So if you're new to this field, this is a very nice paper. It considers a very simple situation where you have 2 ferromagnets separated by an insulating barrier. You regard the 2 ferromagnets as Stoner ferromagnets, so you just assume that you have a Fermi sea where you have where you have a magnetic field, an internal magnetic field that creates a spin imbalance, and these spin imbalances can be at different angles. And then you allow electrons to traverse this barrier, and you ask how much charge and how much spin goes through that barrier, and and you impose that there should be spins conservation. And this has one of the basic diagrams that you'll see for spin torque. If you have two magnets, A and B, you'll find that there is a torque that causes these two magnets to rotate in the same sense. So the spin current, if the magnets are the same, would be the average of these two spin directions, and the spin transfer torques would tend to rotate the magnetization. So you can see there's an exchange of angular momentum, but it's not exchange of angular momentum between the two magnets. The two magnets rotate in the same sense. So the basic question is, where does that angular momentum come from? And it's not just an exchange between the magnets. So he said this is a new irreversible term in the exchange interaction. There would be an exchange interaction even without any currents, just because electrons can tunnel through the barrier, so there's wave function overlap. And he has also said that this relation says that these effects should be important in samples of small dimension. Small dimension because you need relatively large current densities to create these excitations. And it was in magnetic tunnel junctions that was predicted, and all the original experiments were done on, in fact, spin valves, because you could achieve those were the first samples really where you could achieve the current densities necessary to create the excitations. And as you know, these applications, there's important applications of this. Because the interaction is just on the magnets through which the current flows, you can act on a particular magnetic element. You don't have, so it's a much more direct interaction than a magnetic field interaction caused by a current flow. Okay, so the basic physics can be considered as conservation of angular momentum. You create a spin polarization. That spin polarization interacts with the magnetization of a ferromagnetic layer. That can change the direction of spin in the current, and by conservation of angular momentum, there should be a back reaction on that magnetization. So if there were just exchange between itinerant and background, you'd have a conservation law like this, and a torque associated with the change in the spin orientations in the current. And so the fundamental unit is each electron can deposit h bar over 2, its transverse component of angular momentum, to the background magnetization, and the torque depends on how you polarize the electrons, and of course the flow of charge per unit, number of charges per unit time going through the layer. So you can create this polarization with a second ferromagnet, which is thick enough to not respond strongly or pinned in some way, so it doesn't respond strongly to the torques. So you can set and this also enables you to read out the GMR effect. So through a tunnel or GMR effect, you can read out the effect electrically. So you can both create the torque electrically and you can read it out electrically. You can infer the dynamics, or at least one projection of the dynamics electrically. If you consider then how this is incorporated into the macroscopic equations of motion of a magnet, this is an example for a single magnetic domain. So you can consider MTAP no spatial dependence. It just depends on it's a unit vector representing the magnetization direction. MP is a direction of polarization of the current. This is the new term that was proposed by John Slonczewski. It involves saying that the transverse component, the component of spin polarization perpendicular to the magnetization direction, can be absorbed by the ferromagnetic element, and that can exert a torque. If this MP and H effective are parallel, you have a situation where the spin torque can either oppose or enhance the damping, and if it opposes the damping, then it creates an excitation, and you can have either persistent oscillations, an oscillator, or you can create switching by doing that. So you get instabilities, and there's also a possibility to have terms that are proportional to the polarization, an effective field. And the time scales are set by the precession times, 28 gigahertz per Tesla. So this is what I said, and this torque is strictly zero when the polarization and the magnetization are aligned. So this is a picture of the kind of dynamics, the so-called anti-damping dynamics that you get. If your spin polarization is along the axis of the affected field, for currents larger than a threshold, the green curve shows that the magnetization will spiral up. When it hits the equator, this is for a uniaxial magnet, a magnet with perpendicular anisotropy, for example, it will spiral back down to the reverse state. So the current polarity can determine the final state, and you can determine the threshold current is related, in fact, directly to the anisotropy or to the energy barrier to reversal. And so this shows that there's actually a connection between the stability of the magnet, which was talked about yesterday, and the critical current. That factors, the material factors that come in are the damping and the spin polarization you can achieve. And if you want to make a memory, you need this energy to be at about 60K times the temperature, room temperature, say. And that if you put numbers in, you get that the currents can be 15 microamps, so quite low if you believe this simple model. So this is called anti-damping switching because the spin torque opposes the Gilbert damping. Okay, so this is observable in many geometries. The main requirement is a reasonably high current density. For practical reasons, because you don't want the sample to burn up, and for physics reasons, because you want the spin torque to dominate over the fields that are associated with the current. And so that you can make point contacts. We're going to hear about that today. Oscillators that are based on films. You can make pillars. This would be a geometry where you can observe switching, or you build memory. You can see this in single layers, and very exciting is recently you can create these excitations using the spin Hall effect, which you'll also hear about later today. So you can pass a current laterally, charge current laterally, and that can generate a spin current perpendicular to the layer, and create switching or create an oscillator. And even more recently, you can replace this heavy metal with a topological insulator and exert extremely large torques, which are, say, not well understood, but in which appears the topological insulator surface states couple to the magnetic layers and can exert very large torques on the magnetization. So Hideo, Anya-Braftis, and I reviewed this field in 2012. This was a little bit before some of the activities with topological insulators, but it has a review of some of the physics up to that point and device ideas. Okay, so that. With that introduction, I'll talk about some of the recent things we've been working on. So we've been working on perpendicular magnetic tunnel junctions. So these are junctions in which both magnetic layers, both the layer that creates the polarization of the fixed layer and the free layer out of plane. So this is a nice situation that there's in principle uniaxial anisotropy, so axial symmetry. This is also a case which is of interest for the development of STT-MRAM because you can make very small thermally stable elements using the large perpendicular anisotropy you can get in thin magnetic layers. And you can also get relatively low switching currents in this geometry. So the thermal barrier to reversal, the magnetization, say, rotating toward the equator, is also the barrier that you overcome in spin torque switching, whereas for in-plane layers you have to pay a price in the spin torque of rotating out of the plane, which whereas in the thermal reversal is in plane, so you have higher threshold currents in this geometry. So what's new, at least, and I'm sure this is happening elsewhere, is that the switching current has been lowered to the point now where you can drive these systems and look at the dynamics when you have a driven situation, so where you bias the system at two times the threshold current. And the basic question you could ask is, how does this reversal occur? And there's a very clear prediction of the simple model of a macrospin model, assuming everything rotates coherently. And this is an example from a review article we wrote with Eric and Stefan and others, showing that how the magnetization goes from up to down when you have a current of 2 times the threshold. And the prediction of the macrospin model is the main prediction is that the switching should be on a time scale set by the precession time and the damping. Because of thermal fluctuations, the onset is stochastic, but once it starts, the time scale is well determined. So that's a clear prediction. And the other thing we found in work on spin valves, on perpendicular spin valves, is a very nice scaling between 1 over the time required to switch and the threshold and the current pulse supply. So this is the pulse time, this is the current, and this is the line that marks the 50% probability of switching. And this is, you can view this as a demonstration of the conservation of angular momentum. You need to put a certain amount of charge through the layer in order to switch it. If you do it faster, you can use less current. So I times T is this constant minus some other taking out a part that's associated with the threshold current. Okay, so what about reversal mechanisms in these materials, in perpendicular materials? We've done some modeling study of the thermal reversal, and we found actually that the energy, you'd expect that if this were a single domain, the energy barrier would scale as the volume. And it turns out for small diameters, for fixed thickness, that happens. The energy barrier scales as d squared. But as you get to large diameters, the scaling becomes linear. So there's a crossover, at least a predicted crossover, in the behavior of the energy barrier. And we found that there's a critical length that's associated with the anisotropy of the element that determines when you go from a coherent rotation to a nucleation or a reversal where you propagate through a domain wall. And interestingly, Luke Tama at TDK Headway has seen this now in experiments because they can build MRAM with billions of bits and look at the retention and now probe directly the energy barrier as a function of size. And after we wrote this article, we realized that there was also a group at the LPS who had similar ideas about how the energy barrier should scale. So this is actually shows this was one thing that sets characteristic lengths. And we also know from spatially resolved experiments on spin valves that when you look at spin torque switching, the switching occurs non-uniformly. This is scanning transmission X-ray microscopy showing how showing that the reversal is occurring non-uniformly. Okay, so what in terms of experiments that have been done, say time-resolved experiments, there's work by Thibaut de Voder that's been a thermal regime where he applies a ramp-like current to the sample, looks at switching, and that's at least near or below the threshold current is thermally activated. There's also work we did on in-plane junctions where we apply pulses. And we can see oscillations in the pre-oscillations and then switching oscillations. So our focus here was to do these types of experiments on perpendicular MTJs. And the setup is that we have a magnetic tunnel junction in a coplanar waveguide. We have top electrode, bottom electrode. We couple in a pulse with, it can be less than 100 picosecond rise time. And we have a 20 gigahertz real-time scope. This is all done at room temperature. We also have a low-frequency circuit that allows us to measure the resistance and to check it, and then measure after the pulse, and then to reset with a spin torque. So we time resolve what's going on with the dynamics in this way by the resistance measurement. So this is a fairly standard tunnel junction sample. It's a cobalt iron boron free layer. This is the coercivity, the resistance, and what we do is we take time resolved. We do pulses in cases where we set the state with the magnetic field. So we set a P state, we set an AP state, and we measure the transmission for a 20 nanosecond pulse, and then we apply pulses when we're sitting at the center of the hysteresis loop. And this shows an example of a switching result. So we study switching events at the center, and we extract two things from these measurements. One is the time it takes to get to the half resistance point, which we call the switching time, and then the time it takes to switch, which is the 25 to 75% switch. So those are the things we can get out, and we can get also out statistics. So we can look at thousands of events and up to our patients to how many events we want to look at, and we can acquire the statistics of these transition time and switching time. So this shows a typical result on a 50 nanometer diameter tunnel junction. You can see that you get, for various pulses related now to the 50% switching point for this, for a 20 nanosecond pulse. You can overlay this and get a scope trace, something like you'd see in an old-fashioned scope where you'd have memory. Okay, thanks. I have to talk faster, louder and faster. Louder was never my problem. So you can see that actually the switching is fast, but there is a stochastic time scale. And so you can see there's a broad distribution of switching, of onset times in this case. If you look at the 100 nanometer device, same wafer, you see that the characteristics are quite different. The onset can be almost as close to the time you're applying the pulse, which here is time 0, and then you get a ramp-like behavior. And so the onset now is not as stochastically distributed. You have a ramp-like switching and a narrower distribution of the onset times. So there's a very different behavior. In the experiments we did on spin valves, all we could determine was the switching probability, and we found, and you can do here. You can look at the switching time on the left for P to AP and AP to P, and you can look at the transition time now on the right, and you can see that this has this kind of 1/T behavior, at least on average. But the origin of those two are very different as you change the size. Here the transition time is almost independent of the pulse amplitude. This is the transition time. And here the transition time is a strong function of the pulse amplitude. So that was a bit of a surprise. If you just were able to extract the mean or look at the switching probability, these would look very similar. So you see that you have shorter transition times, and you can have transition times now approaching in the nanosecond range. So if you look at the switching time versus pulse voltage for several different diameters, there's a pretty good overlap. You can overlay a 1/T dependence, and that fits to the point where you're at 1, so where most of the switching is a pretty good guide to, at least a pretty good fit to the point where the switching probability is close to 1, and then you see deviations. And then you see the transition time is a function of the device size, and a strong function in terms of for the AP to P transition. So this is what I'll say. And if you were to say that this ramp-like behavior was associated with a nucleation phenomenon, you'd get domain velocities about 20 meters per second, 20 to 60 meters per second, depending on the pulse amplitude. And so in both cases, independent of the size and for all the junctions we studied, as you increase the pulse amplitude, the transition time decreases and approaches this nanosecond scale. And one thing you also see is sometimes you have delayed events. In fact, cases where the transition time is deviating from this 1/T, or it greatly exceeds that of the smaller devices. And what you can do then is look into why that is. At least you can infer that by looking at these kind of scope traces. So looking at pulses and looking at many events. And then what you find is actually there's a propensity for the device to sit in some intermediate resistance state. A small peak here, sometimes more pronounced, sometimes less pronounced. And this appears to be what slows down the reversal in some cases. It's not a stable state, but it's a state that apparently hinders the reversal. In other words, when I say not stable, I mean when we measure at the microsecond scale, it's not in that intermediate resistance state. It's either in the high or the low resistance state. So what is the interpretation we have? Well, I'd say that certainly for the larger samples, for this above 50 nanometers, the macrospin model is not describing the data. We would expect really a very weak variation of the transition time on diameter of the device. And we'd say that for these sizes, greater sizes, it suggests we're seeing a nucleation and growth phenomena, and sometimes the domains are getting pinned. And it seems that in fact this is close. Maybe this may be the scale. We need to do more studies. We now have arrays of junctions that are 20 nanometers in diameter. So we have a ways to go now to look down at the smaller sizes. But it seems that there is a change in the behavior at a scale near this scale which we predicted from the for thermal activation. That may be a coincidence. We'll have to see. Okay, so now I'm probably out of time. Okay, but I want to say one more thing in 1 minute, because especially since this was spoken about yesterday. The idea of using spin-polarized electrons that are perpendicular to the magnetization. And I'll mention that if you want to go faster, you have to use a precession in some way. And this is one way to go much faster, because you can generate, if the spins are polarized perpendicular, you can generate much larger internal fields and much faster precession, in fact. So I'll mention that Daniele Pina, when he was at NYU, developed a very nice model for samples of this type, where you have a polarizer, an in-plane layer, and a reference layer. I don't have time to probably tell you much about it, but there are two types of orbits. They're the orbits you heard about yesterday. Those are orbits around the easy axis, the red orbits that you excite with small amplitudes. And they're blue orbits. These are the outer plane orbits. These are the fast orbits that get you from left to right quickly. And there's a line that separates those orbits. If the spin polarization, the net spin polarization angle is in that upper zone, you can have precessional switching. And if it's in the lower zone, you can have so-called direct switching. And Daniele came up with a beautiful geometric model for that behavior. That is, all depends on essentially where this separatrix is between the two types of orbits and where the net spin polarization acting on the free layer is. And that's published in these series of papers. We've also learned that although this switching is precessional, that is, therefore it should depend very sensitively on the time you apply the pulse, you can also make it deterministic through the shaping, pulse shaping. And maybe you can ask Daniele how to do that. So these are the samples we made. They're spin valves, and these are some of the results we've gotten pretty recently. These results at low temperature, 4.2 Kelvin with a probe station where we can apply pulses. This was initially done. This work is done at BBN by Graham Rollins, who's in that group, and we've been able to see basically on-off. This is pulse amplitude time and switching in about 200 picoseconds. This is a trace of the switching probabilities for P to AP and AP to P. So you can get very, very fast switching, and you get these bands that depend on the pulse amplitude. The spacing here is still larger than you'd expect from a macrospin model. You'd expect the time scales to be about a factor of 4 lower in a macrospin model. These are 50 by 100 nanometer cobalt iron boron 3 layers. Okay, so I think I almost made it, sorry. I hope I've given you some idea of spin torques and the background there, and told you that some of the things now we can do with tunnel junctions and with precessional switching, depending on how you act on the anisotropy of the magnetic layers. Thank you.